can see that the particle age is really not much different really than the absolute age, which is very common, and it basically does the same thing. Goes into the next event, flips over. So if we wanted this to act 20 frames after the event took place, we would use event duration, which is pretty standard, and that allows, obviously when the particle comes in, the count is reset, and 20 frames after the particles entered the event, it has to reach this orientation, which is a much more sort of lenient way of doing things. There you are, you see there's enough time to actually ease into the orientation quite nicely based on the original rotation. So that's actually much smoother. As you've seen, we've defined a duration. That can be any value that you want. There we are. If we increase it, it's now got 40 frames. And after 40 frames, they actually transition into the next event, as you can see. And the next option is a variation on that. So we could actually put in a 10 frame variation, and that will be either way of that number. So now you can see we get a softer edge to transition. If I increase that, obviously we'll get a softer and softer edge. And obviously the particles will try and reach that orientation by that value, whatever that random value is. So you'll see some will spin faster than others to try and reach the orientation, and when they do, they get sent to the next event. Others will spin a lot slower to try and get there. So there you go, that's what variation does. The next group we have is the target rotation, and you can see you've got two choices here. You've either got constant or changing, and this group allows you to define whether the final orientation for the particle to meet is defined once when it enters the event with constant, which you can see is the default, or if it's allowed to change from integration step to integration step with changing. Of course, if you do use changing, be aware that this may cause your particle's orientation to flutter somewhat, as you are in effect giving it new orders on each integration step, and that can cause, as it were, the particle to have some sort of indecision to it. So you've got to be careful that you don't give it a wildly varying target to meet if you've got changing turned on. If we go into the next group, we have the target rotation spin, and this group allows you to define how the particle should match its inherited spin value, or indeed to define a new spin rate. You can see you've got a tick box here called match initial spin, and this option will make the angular velocity, or the spin, match that of the particle when it entered the event. If you wish to define a new rate, untick this box and use the following spin rate parameter. So for instance, if we set ourselves a very high spin rate, there we are. When they enter the event, you can see the particles are spinning at a certain speed, and then they enter the event and they'll actually spin a lot faster. They won't use the original spin anymore. There you go. Now, if I wanted to match the original spin, you can just use that and it'll actually do that. On top of that, you can see you've got variation, which you can see in this case doesn't actually seem to do anything, and you've also got ease in, which should actually do something. Yeah, you can see it's actually causing the particles to ease in to their final orientation. There you go. So I'll just put these back down to 0 again. As I said, if you turn off match initial spin, you then have access to the spin rate parameter, and when this is available, you can use this parameter to define the spin rate of the particle when it reaches its new orientation. So if we, there it goes spinning around, then when it reaches its new orientation, as you can see, it's got that fast spin rate. If we make it a little bit ridiculous, it will make this a little bit more obvious, I think. There we go. There you go, you can see the particles when they enter. By the time they meet their final orientation, they've revved up to that spin speed, which you can see is very, very high. So there you go, and as I said, if you turn on match initial spin, you can see it'll actually keep the original spin value. It'll try and match that when it reaches the end of the test. Now, if I put this value down to something a little bit more reasonable, there we go, you can use the variation, and again, if we put that up quite a bit, because obviously we've got quite a high spin rate, so to have any noticeable variation we need quite a big value here. If I put that so it's actually just above it, there we go. So you can see now that the particles spin round and there'll be a lot of variation. You'll notice some of the particles are spinning very slowly, others are spinning reasonably fast, and that's because we have quite a wide range here. We have 167 and plus minus 158, so obviously that's near 0, and we'll also have values near 300. So we've got, and that is actually the target spin rate that it'll actually reach when it reaches its target orientation. As I've just shown you earlier, you've got an ease in value here, and that will actually cause the particles to ease into that final orientation before they get sent on to the next test. As you can see, they actually slow down into it to give you more of a gradual transition. In the final group, transition end, we have the parameter stop spinning, and when this tick box is active, the particles will actually cease spinning when they reach their new orientation at the end of the duration period. This option takes effect if the test true option is active or not. So let's just show you that. So there you go, particles spin round, they reach the orientation, and they stick there, as you can see. Now that's a little bit hard, and this is probably where the ease in comes into place. So they reach that orientation and they stop dead. Whereas if we used ease in, obviously they'd ease into that orientation, and that wouldn't actually look quite as hard as it does. So there you go. So they actually ease into that orientation, they slow down slightly as they get there. Then they keep that orientation. So that's it, that's the rotation operator. As you can see, it's twofold. It's one of these hybrid tests. It will manipulate our particles, it'll change their orientation to actually reach a value that it then tests upon, and as you can see, then you have the test, and it's implicit in the actual test itself. You don't actually have to set up any real parameters for it. You set a duration that you give your particles to actually reach the new orientation. You assign the orientation to the particles using a following rotation operator or a script operator that sets up the rotation angle for each particle. And then it has this duration to actually reach that orientation, and when it reaches it, the test is true unless this tick box is turned off. Then you have these parameters here to actually just finesse the rate of the spin after the test and so forth, and you also have the ability to stop spinning when you reach the target value. Okay, so that's it for this test. Let's move on to the next test, which is the scale test.